You know, behind almost every huge scientific breakthrough made with Python, we're talking imaging a black hole, detecting gravitational waves, there's this one foundational library doing all the heavy lifting. It's called NumPy, and it's the engine that turned a simple, friendly scripting language into an absolute powerhouse for science.
All right, so here's our game plan. We're going to start with the core problem NumPy was even built to solve. Then we'll get into its brilliant solution, the ndarray. After that, we'll see how its design created an entire ecosystem. And finally, we'll see how it all comes together to help us make, well, cosmic discoveries. So let's start with the central conflict here. Python is famous for being easy to learn and write. Developers just love it. But when it comes to the heavy-duty number crunching that science demands, that very user-friendliness comes with a massive performance penalty.
So what's the deal? Why does native Python just grind to a halt when you throw millions of calculations at it? Well, the answer is kind of fascinating, and it all comes down to how it handles a simple list of numbers.
You see, a regular Python list isn't this nice, neat block of data. Not at all. It's actually an array of pointers, and each of those pointers points to a completely different spot in your computer's memory where a full-blown Python object lives. So when you do something simple, like add two lists together, Python has to follow every single pointer, check the type of each object to make sure it can do the math, and then finally perform the calculation. Doing that over and over millions of times, it creates a crippling amount of overhead.
So how do you fix a bottleneck like that? Well, this brings us to NumPy's brilliant solution. It's a single, powerful, purpose-built data structure that just completely sidesteps Python's limitations.
And here it is. Meet the ndarray. This is the architectural hero of our story. Instead of a bunch of scattered pointers, an ndarray is one single, dense, continuous block of raw memory, kind of like a C array. Every single element is the same data type, all packed in there tightly together. And that one design choice is a total game changer because it gets rid of all that overhead. No more type checking, no more pointer chasing. The CPU can just rip right through the data at full speed.
And this table really just lays it all out. A Python list is heterogeneous. You can stick anything in it. An ndarray is homogeneous. Everything's got to be the same type. But the memory layout, that's the key. Scattered pointers versus a contiguous block. And that flows right into performance. Slow Python versus lightning-fast compiled C. A Python list is a flexible jack-of-all-trades, but the ndarray is a specialist. It gives up all that flexibility for pure, raw, unadulterated speed.
And every one of these ndarrays carries its own blueprint. It has essential info, like its shape, the data type of its elements, and a direct pointer to that block of memory stored right there with it. This lets NumPy know exactly what it's dealing with, so it can operate with maximum efficiency. Okay, so we've got this incredibly efficient data structure, but the real magic comes from how NumPy actually uses it. These are its computational superpowers.
The first and most important superpower is called vectorization. Basically, instead of writing a slow Python for loop that goes through each item one by one, you write a single, clean expression that tells NumPy to operate on the entire array all at once. What this does is it pushes that slow loop out of Python and down into highly optimized, pre-compiled C code. And this just says it all, doesn't it? On the left, you have a slow, clunky, multi-line Python loop. On the right, you have one elegant line of NumPy code. C equals A times B. That's it? It's not just way easier to read, it's orders of magnitude faster. It's beautiful.
NumPy's second superpower is broadcasting. And this is, well, it's pretty much magic. It's a set of smart rules that lets you do math on arrays that don't even have the same shape. For example, you can add a single number to every element in a giant array without writing a loop. NumPy just kind of stretches that number to match the bigger array without actually using any more memory. It makes your code incredibly flexible and just intuitive.
So here's the thing. NumPy's impact isn't just that it's fast. Its greatest contribution was becoming the universal standard, the bedrock that allowed an entire ecosystem of other powerful tools to even exist. And this quote just captures it perfectly. The ndarray became the common currency, the lingua franca, the universal language for data. It created a standard that all the other libraries could count on, making sure they could all talk to each other without a problem. And because they all spoke the same language, these titans of the Python world could flourish. You've got SciPy for advanced math, Pandas for data analysis, matplotlib for plotting, and Scikit-learn for machine learning. All of them are built on top of that same high-performance foundation that NumPy provides. They're constantly passing these ndarrays back and forth, creating this incredibly powerful and fluid workflow.
Okay, so we've covered the theory, we've covered the architecture. Let's see how this all comes together in the real world to fuel one of the most incredible scientific discoveries of our time. Back in 2015, the LIGO experiment set out to prove something Einstein had predicted a century earlier, the existence of gravitational waves. The problem was, well, it was monumental. The signal from two colliding black holes would be this impossibly tiny ripple, buried in a chaotic sea of noise that was literally billions of times stronger. It's like trying to hear a pin drop in the middle of a hurricane. So finding that signal was only possible with massive computation, and NumPy was at the absolute heart of it. The raw data from the detectors was loaded into huge NumPy arrays for filtering. Then they had to cross-correlate that data against hundreds of thousands of template waveforms, another massive set of array operations. Finally, they used statistical analysis on ndarrays to figure out if what they saw was real. NumPy's performance wasn't just helpful here, it was absolutely essential. The discovery couldn't have happened without it. And that's the payoff, right? This historic achievement, confirming a core piece of general relativity, was powered by the exact same principles of vectorization and efficient array computing that we've been talking about. It's a straight line from a clever data structure all the way to understanding the universe.
So NumPy was the perfect architectural answer for making Python fast on CPUs. It was a masterpiece. But today, we're moving into an era of GPUs, TPUs, and all sorts of new hardware. And that leaves us with a really fascinating question to think about. What's going to be the next lingua franca? What's going to be the next NumPy that unlocks the next generation of scientific discovery?